All right, so today we'll finish up chapter 13, the last of the material for the first exam. So again, hopefully everybody's all set up and scheduled for that. It'll be open June 1st through 5th on Examity. And so today is going to be a lot of calculations. Section 13.3 has quite a bit of stuff. 13.4, not so much, but I guess might as well get into it. And so the first section, 13.3, talks about a couple of things, arc length and curvature. And so arc length is just a fancy way of saying it's how long the curve is. So if you were bending this cable in the shape of your curve, you know, how much cable does it take? And so a curve you want to think of, remember, as a one-dimensional object. So the appropriate way to measure a curve is how long it is. So if you were, you know, buying a curve at the curve store, you'd be paying per foot or per meter or something like that. So length of curve is arc length. And so the other way you could think about it, so we mentioned that you could think of r of t as being the position of a particle at time t. So if you're in the xy plane, you could think, okay, you're driving your car around in the plane. Or if you're in space, you know, you're driving an airplane or a spaceship around in space. And so the length of your trajectory is just going to be the distance traveled, and it's going to be what your odometer says, right? Your odometer on your car tells you the distance you've traveled along your path. And so anyway, if we have a curve given by the vector function r of t, the length of the curve between the points r of a and r of b is going to be the integral from a to b of the length of r prime of t dt. So let's say this is your curve C that we're talking about. Remember, anytime we are using r, we're talking about a position vector. Position vector just means it's starting at the origin. So our starting point here has position vector r of a. Our ending point here has position vector r of b. And the length of this curve here, however long you travel along the curve, that's your arc length. Okay, and so why is this the formula? Let's see if we can understand. And so this is neat. It'll tie together some ideas from yesterday when we started talking about derivatives of vector functions and things like that. And so I guess what we want to do, let's focus on the length of a small piece. Okay, so let's zoom in and look at this small piece right here. So maybe I'll be a little bit more careful as to which piece I'm looking at. So we have this blue thing here, and then this pink line segment like that. Okay, and so the idea, just like in Calc 1, if you remember, the whole idea of tangent lines was if you zoom in really close on a curve, it almost looks like a straight line. And the concept of derivative is the slope of that line when you zoom in really far. And so, okay, the idea is that this is a small piece that looks like that. And so if you zoom in far enough, that the length of that small piece is approximately the length of that straight segment. So just like at Calc 1, when you zoom in far enough, there's not too much deviation between the line segment and the blue curve. So the length of those two are approximately the same. And so then let's see if we can figure out how long the pink line segment is. And so I guess let's say that this point here corresponds to the point with position vector, let's say r of t. And we'll say that this here is r of t plus delta t, where delta t is some small number. Maybe it's 0.1 or something like that. So I guess drawing that in on this picture, you know, this position vector is r of t, and this position vector is r of t plus delta t. Okay. And so what that means is that this vector here, I'll just make it pink as well. The vector pointing from r of t to r of t plus delta t, those points, is going to be r of t plus delta t minus r of t. The whole idea of vector addition would be that, yeah, if I add r of t plus r of t plus delta t minus r of t, I'm going to get r of t plus delta t. So that's just sort of vector addition / subtraction, however you want to think about it. And so the length of that piece is the straight line segment piece is the length of r of t plus delta t minus r of t. Okay. And so now we could go back to yesterday. So yesterday we talked about that the definition of r prime of t is the limit as, we called it h yesterday, but we could call it delta t today, r of t plus delta t minus r of t all over delta t. That, remember Calc 1, the whole definition of derivative as the limit of a difference quotient as the change in the input goes to 0. And so that's our definition of r prime, which means that for small delta t, you could rearrange this equation to get that r prime of t times delta t is approximately r of t plus delta t minus r of t. So intuitively, just like, Calc 1, remember change in y is approximately derivative times change in x. So change in r is approximately derivative of r times change in t. So if you substitute that in here, that'll be approximately equal to the length of r prime of t, and then assume delta t is some small positive number, so I can pull that constant factor out there. So when you zoom in really close on a little small piece, the length of that blue piece is approximately length of r prime times delta t. So the total arc length should approximately be, add up a bunch of these small pieces, right? So we just focused on one piece so far. So let's add up the approximate length of all these pieces, all those other little pink line segments you see in the picture. And so now when you take the limit as delta t goes to 0, this is going to end up being the integral of length of r prime of t dt. That this Riemann sum, as you take the limit as the width of these subintervals goes to 0, that's what a definite integral is, the limit of Riemann sums. And so that's our arc length formula. And so later on today, we will talk about how, we already talked about how you could think of r as position. So when we get into section 13.4, we'll talk about that. In that case, r prime is the velocity vector of your particle, and the length of velocity is what we call speed. So essentially, this formula for arc length is saying that the distance traveled on curve is the integral of speed, which makes sense. That's when I said a few minutes ago that you could think of arc length as your odometer. That's exactly what your odometer is doing. When you drive your car, the odometer is giving you your definite integral of your speedometer as a function of time, right? Your speedometer has units miles per hour. Your odometer has units miles. So yeah, if we want to think units, then I guess we should use SI units, just so we don't get laughed at by scientists. Speed has units, say, meters per second. dt you want to think of as having units of seconds, and so you end up getting something with units meters, which is the distance you've traveled. And so before we do an example of arc length, I just want to warn you that a lot of things in math, you have to be careful the order in which you do things. So some things, it doesn't matter which order you do it in. So for example, you could think of the distributive law for number arithmetic as saying whether you add the numbers then multiply by a, or do the multiplying and then the adding, it doesn't matter which way you do it in. But not everything is like that. So for example, like cosine of a plus b, or whatever, let's just do it with square roots. Square root of a plus b absolutely is not square root of a plus square root of b. The order in which you apply the square root and the order in which you do the addition matters. And so I like to think about it that it's not so surprising. I mean, I always get frustrated when people always think that order doesn't matter, to the point where I think this actually colloquially is sometimes referred to as the freshman's dream, that the order that you do the square root and the order in which you do the addition doesn't make a difference. Well, it absolutely does make a difference. And for a real world example of where it does make a difference is, let's say when you're putting on your shoes and your socks today, right? If you put your socks on first, then your shoes, that's what you want. But if you put your shoes on first and then your socks, that's quite different. So math, just like the real world, it shouldn't be so surprising that the order in which you do things sometimes matters, right? In the real world, it doesn't always matter. Whether you put your shirt on or your pants on first or second, you're still dressed at the end, but some things, the order matters. And so, okay, as far as this arc length formula goes, what are the two things that we're doing? Well, we're taking the length of the vector r prime, and then we're doing an integral. And so you do have to make sure you do it in the appropriate order. If you put your your shoes on before your socks, i.e. if you do the integration before you take the length, the fundamental theorem of calculus says that the integral from a to b of r prime is just the change in r. And so visually what's happening there is you're just, you're getting the crow flying distance between the 2 points, right? Because if this is your curve r of t, then if I do r of b minus r of a, that's this red vector here. That, you know, at t equals a, you're at this point, at t equals b, you're at that point. So the vector r of a minus r of b is just that direct, as the crow flies path from the start to the end. And so if you do the integration first and then take the length, you're just getting that length. Whereas if we want to actually get the distance traveled along the curve, then you have to be careful and do this first. Yeah. So again, be careful. You know, anytime you're doing a math thing, whether it's in this class or another class, you have to wonder, does the order matter? For number multiplication, it's just like your shirt and your pants. Who cares which one you do first? You're still dressed at the end of it. So whether you do the addition first and then the multiplying, or the multiplying and then the addition, doesn't matter. But other things, it does matter. So anyway, quick example. So find the length of the helix given by r of t is cosine t, t sine t, between the points 1, 0, 0 and 1, 4 pi 0. Okay, and so we talked yesterday about the importance of finding the t-value that spits out given points for a lot of these situations. So when you look at this formula, which I guess I could just scroll up here, I need to figure out what a and b are. And so a and b are going to correspond to whatever the t-values are for these given start and end points. You know, a and b are just numbers here. They're not vectors. They're not points. They're just numbers. And so I have to look at 1, 0, 0, and okay, what value of t makes r of t equal to 1, 0, 0? Well, without too much trouble, you see that that's t equals 0. And then for 1, 4 pi 0, we have to ask ourselves, okay, what value of t makes cosine t, t sine t equal to 1, 4 pi 0? And yeah, turns out it's 4 pi. So like I said yesterday, you have to find something that works for all three. If you can't, then I lied to you and that point isn't actually on the curve. But as we could see, 1, 0, 0, 1, 4 pi 0 actually both are on this curve, so we're all set. And so, okay, I guess let's do the other stuff we have to do. I have to get r prime of t, which is minus sine t, 1 cosine t. I have to take the length of r prime of t, which is the square root of sine squared t plus 1 plus cosine squared t. So be careful. See a lot of careless mistakes for these types of things where people do the Pythagorean theorem incorrectly. But cosine squared t plus sine squared t is 1, so I'm left with square root of 1 plus 1, so square root of 2. And then my arc length is the integral from 0 to 4 pi of square root of 2 dt, which that's a pretty easy integral to do. You just get 4 pi times the square root of 2. And that's that. So sometimes you have to find the t values like we did here, but then other than that, you're just getting r prime, length of r prime, and integrating that. So anyway, that integral wasn't so bad. You shouldn't expect all of the questions to be so straightforward once you get here. You might have something that depends on t. We got lucky in that this length r prime was just square root of 2, no matter what t was. So be prepared for having to do a little bit more work on that antiderivative. But if you think about the formula for the length of r prime, it's always going to involve a square root. And so if you have the square root of something messy, it's possible that you could have some real trouble getting an antiderivative, right? Like if I asked you to do the antiderivative of like t to the 4th plus, t to the 5th plus 7, I don't know how to do that, right? I don't have the derivative of the inside that I would need for a substitution to work. And I guess I should just get this out of the way. As far as integration techniques that you need to remember from previous courses, I'd say know how to do substitution. There might be a couple homework problems that require the use of integration by parts, but we don't usually put that on quizzes or exams. So yeah, quizzes, exams, you won't have to do integration by parts. You won't have to do partial fractions. You won't have to do trig substitution. Pretty much the only integration technique that you'll need for this course is substitution. And so something like this, I can't get a substitution to work out because I don't have the derivative of the inside function. And so basically what that means is that any arc length question we ask you to do, there's going to have to be some trick that works. So for example, this Pythagorean theorem for cosine squared and sine squared, that comes up fairly often, so be on the lookout for that. The other way you could get lucky here is if it happens that this stuff under the square root is a perfect square, so something like t squared plus 2t plus 1, that could be factored as t plus 1 squared. So be on the lookout for that. And so you'll see a few of those possibilities on the homework. So in order to be able to do this antiderivative, something is going to have to work out nicely with regards to that square root. So keep that in mind. All right, so let's continue talking about arc length. And so what we need to talk about next is something called the arc length function. And so essentially it's the same as the arc length formula that we just talked about, except we're going to leave it as a function of t. That in our previous example, we got numbers for a and b, and that was just the arc length of a specific part of the curve, which, okay, our helix would have looked something like that, so we're getting the length of 2 loops around for that particular one. But then we can sometimes leave the arc length as a function of t. So, okay, this formula looks a little weird. Remember yesterday I said you want to use a different integration variable, that it's bad form to have your integration variable also be doing something else in the same equation. So you could use u, you could use v, you could use basically anything, just don't use t if t is the independent variable for this function that we're talking about. And so think of a as still a number. So anyway, let's say we're in our car, and once it's a o'clock, we'll zero out our odometer. And then from then on, s of t, so we'll use s to indicate arc length. So s is going to be the distance you've traveled between time equals a and time equals t. And so, yeah, just imagine, okay, let's get in our car at noon. So a is 12 o'clock or whatever. We zero our odometer, and then the function s of t is how far we've driven by time t. And so here's a picture indicating what's going on. So when you're at the position r of a, zero out your odometer on your airplane or spaceship, whatever you want to think of, because it looks like we're in R3. So for example, S of A is 0, right? If I zero my odometer at time equals A, then my odometer says 0 at time equals A. That's what S of A equals 0 means. And then, okay, all this is doing is telling you that at time t, I've traveled S of t units, that my odometer says S of t. Okay. And so let's find the arc length function for this same helix that we did, starting at t equals 0. So this a is always going to be a number that you have to be told. It's telling you what time do you zero your odometer. And so it says to zero our odometer at t equals 0. So essentially what we're on the lookout for is S of t is the integral from 0 to t, length r prime, and then I shouldn't use t, I should use a different integration variable, so let's just use u. And we saw in the previous example that this helix, the length of r prime was always square root of 2. And so this integral from 0 to t of square root of 2 is pretty easy. It's square root of 2 times t. So again, be prepared for this to be a little more difficult. It's still going to be possible using, at most, integration by substitution. But this one's particularly nice because it turns out it's constant speed, that the length of r prime is square root of 2, doesn't depend on time. But yeah, that's it for arc length function. Integrate from 0 to t of the length of r prime, and that's it. Okay, so why do we care about this? What's going on here? So this arc length function is a stepping stone for getting something called the arc length parametrization for a curve. And so this is where we kind of have to think, okay, what is this parametrization r of t doing in the first place? So I mentioned yesterday, you want to think of t as time and r as being your position as a function of time. So something that is true is that, remember, there's infinitely many different parametrizations for any given curve. So we can have two different time parametrizations for our curve. So for example, let's say you're driving on, next fall, you're coming back to State College and you're tracing out your path as far as how that goes. So for example, let's say that, at t equals 0, you start at wherever you're coming from. And then, okay, so t equals 1, t equals 2, you're there. But then let's say now you get on the highway, so at t equals 3, you're there, t equals 4, you're here. And then let's say that you decided to come up in the middle of August, so let's say a couple of weeks before classes start. So there's not much traffic, and you get to State College within, let's say, 6 hours. Okay, so that's, you could think of time parameterization as basically position as a function of time. And so, okay, tying it back to what we were talking about yesterday, there's different ways, different parameterizations that could give you the same path. So let's say, like I said, you got to State College 2 weeks early before classes, but then let's say you forgot something at home, so you drive back to your parents' house or wherever you were staying for the summer, and you drive back, but now it's the move-in weekend for everybody. So let's say you're just having a really bad trip in addition, so like at t equals 0, you're here, t equals 1, you're here, t equals 2, you're here, t equals 3. But then let's say that there's an accident on the highway. And so you're stuck in some horrible traffic jam on the highway, and then it speeds up again, so t equals 7, you're here, but then it's move-in weekend, so there's horrible traffic in State College as well. And so that's what you want to think of as T time parameterizations as being. It's your position traced out as a function of time. Okay, so what's this concept of arc length parameterization? So with arc length, instead of recording your position as a function of time, you're going to record your position as a function of what your odometer says. And so if instead, as long as you're taking the same path, you're taking the same roads, you're going to get the same arc length parameterization from each of these. So for example, let's say that, I have no idea. Let's say that, okay, maybe this is s equals 0. So you zero out your odometer when you're at your starting point. And then, I don't know, let's say, assuming a speed limit on the highway of 60 miles an hour, maybe this right here is like 60 miles away. And that this is another 60 miles away, another 60 miles away, another 60 miles away. And let's say that you live, or you were coming from 300 miles away from State College. And so this idea of this arc length parameterization is that it's more intrinsic to the roads that you're taking, the curve itself. That time parameterizations care about traffic, or let's just say they're affected by traffic. They're affected by whether you speed up, slow down, and things like that. But if you instead you record your latitude and longitude as a function of what your odometer says, then you're always going to get the same arc length parameterization as long as you zero your odometer where you're coming from and you take the same roads that you get. So the way you want to think about this arc length parameterization is a nice standardized way to trace out a curve. That you're not allowing speed variability to come into play. Essentially, you're just tracing out your curve according to how far you've traveled along that curve. And so that's what I meant here when I said intrinsic to the path. That it doesn't contain your speed information or your traffic information. It just traces it out like that. Okay, and so as far as getting an arc length parameterization, there's sort of 3 steps, and I explain them here, but let's just write it in terms of 3 steps. So step 1 is to get your get s of t, guessed. So get your arc length function for this situation. I'll answer your question in a second. So get S of t. Step 2, invert this function to get t in terms of s. And then step 3 is to plug back in to the original r of t. So, okay, so the question is this only relevant when dealing with real-world examples, or can lines move at different speeds when working with more abstract problems? Sorry, okay. It's true. So, I mean, I'm trying to tie it to the real world just to help explain what on earth is going on. This example that we've been working with so far is kind of special, that this length r prime of t doesn't depend on t. And so a property that this happens to have is that this traces out the curve at a constant speed. But if you're not lucky like this, you can perhaps not have constant speed. So let me speed up here, or let's go here. So we'll get to this example in a while. We'll get to curvature in a while, but something that we'll have to do is get r prime of t is 1, 2t, 3t squared. And so the length of r prime of t is square root of 1 plus 4t squared plus 9t to the 4th. And so this is an increasing function of t, which means that if I were to trace this out, it starts off when t equals 0, this is speed 1, but then it kind of speeds up. So I don't even know what this looks like, but it's going to go look like this, speed up. And all of this is basically motivating this idea of curvature that we're working our way towards. And if we take derivatives with respect to t, we're asking ourselves, how does something change with time? But it turns out I might instead want to talk about how do things change with respect to distance traveled. And so that's really why we're getting into this, that there's some things that we're going to want to do where we imagine, instead of this being, you know, slow and then fast and then slow and then fast and then slow and then fast, that we'd prefer to have it just be at a nice uniform rate. That essentially how curved this curve is shouldn't care how fast I'm tracing it out. It should be, well, how curved it is. Like, what's this shape doing as I trace it out at a constant speed? And so having something where it's like this and like that, and like this and like that, it can like screw things up. So anyway, long answer. But yeah, if you pick a random r of t, it's probably not going to have constant speed. And there's some things where we want to have it have constant speed, and this arc length parametrization is basically a way to accomplish that. That we want to forget about traffic, right? Because intuitively, the idea of how many turns you're taking, it's going to depend on, or how sharp of a turn you're taking. It doesn't, the sharpness of your turn doesn't care about how fast you're taking it. It's really just, you know, how much is your direction changing by? You know, you're going east and then north. You're not asking how quickly that change is happening in time, but instead with distance. So that's sort of what we're building towards. Okay, so anyway, let's get the arc length parametrization for this situation here. And maybe I'll just write it here. So arc length parametrization sort of converts the parametrization to have constant speed, that you're sort of deleting the traffic variability. And so constant speed in the sense that if we call RAL of S, or arc length parameterization, it turns out that that's always actually going to be speed 1. So it's a nice standard way to trace out our curve. So let's take a look. So to get the arc length parameterization, the first step is to get the arc length function, which we saw a few minutes ago was square root of 2 times t. And so step 2 is, this is odometer as a function of time. We want to find time as a function of odometer. And so again, be prepared for this to have a couple more steps for more complicated things, but just solve for t in terms of s. In this particular case, it's just as simple as dividing by square root of 2. And then step 3, plug back into the original r of t. So we define the arc length parameterization of s to be the original r of t, but now I plug in for s in terms of t. So this is what we define it to be. And then we get cosine of s over square root of 2, s over square root of 2, sine of s over square root of 2. And so to now confirm that it did what we wanted it to do, let's take the derivative with respect to s of this. So this is going to be minus sine of s over root 2 over root 2, comma 1 over root 2, comma cosine of s over root 2 over root 2. And so the length RAL prime of s is going to be the square root of, well, sine squared s over root 2 over 2 plus 1/2 plus cosine squared of s over root 2 over 2, which Pythagorean theorem tells you is square root of 1/2 plus 1/2, which of course then is 1. So essentially, yeah, think of this arc length parameterization as you're deleting the traffic and speed information. And instead of tracing it out at whatever speed it is, maybe it speeds up, it slows down, it speeds up, it slows down, you're converting it to, I'm just going to cover 1 centimeter per second when I draw this curve. So you're talking about the curve in a more standard way. And so now we can start talking about curvature. So this idea of curvature is pretty much exactly what it sounds like. It's going to be a measure of how curved your curve is. And so we're going to define curvature to be this non-negative scalar kappa. And in general, it depends on which point of the curve we're talking about. So zero curvature is going to be exactly what you expect. So if you're, for a while, if your curve is a perfectly straight line, we're going to say that that's not curved at all, right? A line is the worst curve there is because it's not curved. And so zero curvature corresponds to straight. And then let's say it starts to bend ever so slightly. So it's not a straight line, but it's not that curved. So let's say you have small positive curvature at that point. But then let's say after that, it gets very curved. Then we would say that has larger curvature. So essentially all it is saying you're driving your car, how extreme of a turn was it? And so that's all curvature is how curved the curve is. So when my wire is like this, it's not very curved, but if I do this and bend it a lot more, then it's pretty curved. So that's all we're trying to do. And so now let's start to think about how we could measure this. So should we define curvature to be? Well, what does it mean to be curved? It means that the direction of the curve is changing, right? So if you remember yesterday, we were talking about how the tangent vector r prime somehow encodes the direction of the curve. So if we want to measure the change in direction, sort of the first thing that comes to mind, change in direction, change in r prime, should I just do like r double prime, which that's still a vector? We already said we wanted curvature to be a scalar. So should I take curvature to be the length of r double prime? And it turns out I don't want to have that be the case, because we want the curvature of a straight line piece to be 0, but it's possible to accelerate in a straight line, right? Let's say that your particle starts here at t equals 0, and then at t equals 1, let's say it's there. Well, I guess it would be here at t equals 1, so that's annoying, sorry. Let's draw that again. Too much erasing. So we have a straight line path. Let's say that at t equals 1, it's here, but then at t equals 2, it's all the way there. So for example, this, and it keeps speeding up. So like maybe this first red vector is r prime of 0, this is r prime of 1, this is r prime of 2. So it's accelerating in a straight line, but these vectors are changing, right? R prime, its direction isn't changing, but it is getting longer. So r double prime isn't 0 in this case, but we already said that we want the curvature to be 0 if it's moving in a straight line. So this is why we don't want to use r double prime as our definition of curvature. Okay. So what else could we use? So something we could do is we could try and take out the length of these tangent vectors. And so the book in section 13.2 actually talks about something called the unit tangent vector. I didn't talk about it yesterday because it wasn't so important, but we can call this unit tangent vector just the tangent vector made into a unit vector, which, how do you make a unit vector? You divide by the length of that vector. So if I want to change r prime into length 1, I take r prime over the length of r prime. And so, okay, that's what we'll call capital bold T of t, is unit tangent vector. So, okay, to measure the change in direction, should we use t prime of t or the length of t prime of t? And the answer is not quite. So it does take care of our straight line question. That let's do the same thing we had a second ago, where this was t equals 0, this is t equals 1, but then it speeds up, and so t equals 2 is there. So I'll use a different color than red. I don't know what these, yeah, okay, so this should be t of 0. But then t of 1, no matter what, these t's are all unit vectors, so they can't get longer. So like t of 2 is length 1, t of 1 is length 1, t of 0 is length 1. And so we see that in this case, you know, this is okay for lines. That if you have a line, then t prime will be the 0 vector. And so if you take the length of t prime, in that case, you'd get 0. And so curvature would be 0. So that's okay. So we're a little better. That at least this tells us that the curvature of straight lines is 0. Because the direction of the straight line isn't changing, we've sort of taken out the length of r prime by dividing by it. And so, yeah, the direction isn't changing, and the direction is encoded by t. So t's not changing, that's fine. But it turns out that this won't work otherwise, because let's say that I have something like this, where I have a shape that looks like this. So at these 2 points, the curvature should be the same, right? Because intuitively, curvature is how curved the curve is. So if I just sort of took my charging cable here, or even just looked at 2 points like this, like it's about the same amount curved here as here, right? And so the problem is that t prime of t is the derivative of t with respect to time. So maybe like this point here is like t equals, 0, say this is t equals 1, and this is t equals 2. But then let's say it like really slows down so that like this is t equals, 1,000, and this is like t equals 2,000. So it's really screeching to a halt. So this has a much smaller length of t prime of t, because the whole idea is that the change in t is similar, that you're going from here to there. And in that case, that's over a change of 2 hours, let's say. Whereas you're doing the same basic change in direction, but you're doing it over a period of 1,000 hours. And so t prime of t is the change in direction with respect to time. We don't want to measure with respect to time. If I asked you like how curvy of a road it is, your answer shouldn't change based on how fast you went. That there should be something more intrinsic about this idea of curvature. And so essentially what we want to do is measure the change in direction with respect to distance traveled along the curve, not with respect to time. So change in direction divided by how far you've gone. That's what we want to do. So basically, we're going to define curvature to be the length of the derivative of your unit tangent vector t with respect to the arc length s. Okay. And it turns out that this is actually the length of r al double prime of s. Okay. And so then the question is, do I have to parameterize with respect to arc length every time I want to calculate curvature? And the answer is actually no. So parameterizing with respect to arc length in general, that's kind of a pain. We don't want to have to do it if we don't have to. And so, okay, why don't we have to do it? So remember, the arc length function s of t is defined as this definite integral of the length of r prime. And so I think it depends on which textbook you use. I think our textbook calls this the first part of the fundamental theorem of calculus, that when you define s of t to be an integral of r prime, that means the derivative of s is the length of r prime. So s prime of t, or ds dt, is the length of r prime of t. So you could solve for dt ds using the chain rule as the dt dt. It gets confusing, we're using too many t's, but then divided by ds dt, which we saw that ds dt is the length of r prime of t, and so this is we'll call this the first formula for curvature. And so, okay, don't worry so much about it. I tried to motivate this. It's, in general for this course, it's more important that you guys can know and use these formulas as opposed to really understanding where they came from. So if a lot of the previous few minutes were very mysterious, don't worry too much about it. Focus more on these examples and the use of these formulas. So anyway, let's make sure that this is doing what we want it to do. So find the curvature of a circle of radius capital R. Yeah, there's a spider on this desk. I lost him. Okay, hopefully it doesn't freak me out. Okay, so circle of radius R. Let's just do it in the XY plane. It's fine. So we have our circle. We talked yesterday that one way to parameterize this circle of radius R is R cosine t, R sine t. So R prime is minus R sine, R cosine. The length of R prime is, Pythagorean theorem will tell you that it's R. So you'll get R squared cosine squared t plus R squared sine squared t in a square root. And then that means that t of t, the unit tangent vector, remember we just introduced that a few minutes ago, all it is R prime normalized. You end up getting minus sine of t cosine of t, right? Cancel out your radius, capital R. And then t prime of t is minus cosine t minus sine t. And then similarly, when you do the length of t prime of t, Pythagorean theorem is going to tell you that that's 1. And so then curvature as a function of t is, recall, the length of t prime over the length of r prime, so 1 over r, which is good. It sort of does what we want, because what that's telling us is if the radius of our circle is really small, it's a big value for curvature, right? Curvature is 1 over the radius. Whereas if r is big, curvature is small. So that's how you get these idiot flat earthers talking about how the earth is flat. So in this course, we're not going to talk about the curvature of surfaces, but you can. But yeah, the earth is pretty damn big, which means it's not very curved, and then you get these morons who say that it's flat. Well, guess what? It's not, but that's the idea. So hopefully that shows you then that this definition of curvature does intuitively what we want it to do, that to bend a wire into a really small circle, you really have to bend it a lot. It has to be very curved. Whereas if you have a gigantic circle like the surface, like the earth, it's not very curved. It looks almost straight. And there we go. All right. And so I guess then we've been working with this helix equation a few times. I'll just go through this pretty quick. It's pretty much the same calculation that we just did. Remember, we get r prime is minus sine 1 cosine. The length of r prime we've seen before is the square root of 2. Therefore, the unit tangent vector is r prime normalized is minus sine t 1 cosine t over square root of 2. T prime of t is minus cosine t 0 minus sine t over square root of 2. Length of t prime of t is Pythagorean theorem. Again, you'll get 1 over root 2. And so then curvature is the length of t prime over the length of r prime. So length of t prime over the length of r prime gives us 1/2. Okay, so that's our first formula for curvature. And so I guess now we get to a point where I can warn you that calculating T prime can be a pain in the butt sometimes. Because if you look at T, the definition of T has the length of R prime in the denominator. If you have this denominator that's complicated, then taking T prime is going to be a mess. It wasn't a factor here because the Pythagorean theorem magically made the length of R prime square root of 2. So this didn't depend on T. But let's just take a look at a concrete example for when it does so you could see. So I think that's what I was starting a few minutes ago when we jumped ahead. Let's say I'm taking the curvature of this thing. So I start off the same way. I get R prime, I get length of R prime. Now I get T, which again, as always, T is R prime normalized. So it's going to be 1, 2t, 3t squared over the square root of 1 plus 4t squared plus 9t to the 4th. And so you could use the quotient rule 3 times once on each component to get T prime. But I think it's easier to write it as, 1 plus 4t squared plus 9t to the 4th to the minus 1/2 times 1, 2t, 3t squared. And so then T prime of T, you would use the f of T, u of T product rule from what we talked about yesterday. That take care of that denominator as a scalar function multiplying a vector function. But in summary, it's a big mess, right? I don't think any of us is particularly excited to do that or to do the quotient rule on each component, right? Everybody hits the quotient rule. So it turns out there's a way we can get around this. And so what's that going to be? So it turns out we're going to have another formula for curvature. And so I think it's good to know both of these. This one is best when the length of R prime of T doesn't depend on T. And this formula is best when length of R prime of T depends on T. And so I know I always get this question, my brain is full. I only want to memorize one of these. Which one should it be? I'd say if you're only going to do one of them, go with this second one. So yeah, if you want to just remember one of them, I think it's safer to do this second one. So I'll show you where this formula comes from in a second, but let's use it on that same curve that we wussed out of completing here. We did not feel like getting our hands that dirty for this. T prime of T is awful for that. So let's use this new formula here. Okay, so I got to get r prime, which that's the same 1, 2t, 3t squared. I have to get r double prime, which is 0, 2, 6t. I have to get the length of r prime cross r double prime, which ends up being what? 12t squared minus 6t squared is 6t squared. Then I get 0 minus 6t, and then I get 2 minus 0. And that's the cross product. Sorry, that's not the length. The length of the cross product is then square root of 36t to the fourth plus 36t squared plus 4. And then the length of r prime of t we saw before was square root of 1 plus 4t squared plus 9t to the fourth. And so therefore curvature is the length of r prime cross r double prime over the length of r prime cubed. So it ends up being square root of 36t to the fourth plus 36t squared plus 4 all over 1 plus 4t squared plus 9t to the fourth to the 3/2. And so, okay, that was a little tedious. Had to do a cross product, but the calculus was easy. Easier, I would say. Yeah, because calculus, the r prime, r double prime, that was basically no trouble at all. Whereas t prime would have been a huge pain. Okay, and so hopefully that convinces you that that cross product formula is much better when you do have that t dependence for the length of r prime. Okay, so now why is that other formula true? Seems mysterious. So you don't have to know about this, but it follows from stuff we've done in this course before. Sort of ties together a few different ideas. So let's take a look. So the first step is, so I'm going to leave out, the t dependence of everything, just to make it a little bit cleaner for what I'm about to write. So everything depends on t. Yeah, maybe I should just write that instead. So everything is a function of t. So the starting point is, remember our unit tangent vector is r prime normalized. So when I mean everything is a function of t, I'm just being lazy. I'm not writing of t on everything. So anyway, that means that r prime is the length of r prime times t. Okay, so now I'm going to take the derivative of both sides with respect to t to get that r double prime is the length of r prime prime times t plus the length of r prime times t prime. So I used a product rule that we talked about yesterday to get that. Next step is I'm going to do r prime cross this equation. So in the same way that you've been multiplying both sides of an equation by something for years, well, you could take the cross product of both sides of the equation by the same thing. So I get r prime cross r double prime on the left. And then I have r prime prime. I'm going to write it r prime cross t. So I'm going to put the vectors together, right? Because this here is just some scalar. The length of r prime is some scalar function. The derivative of that is some scalar function. So I'm just going to put my vectors together with this cross product. So length of r prime times r prime cross t prime. Okay. And so now let's get creative with some colors. R prime is the tangent vector. T is the unit tangent vector. These are parallel vectors, right? They're parallel vectors, which means that when I take the cross product of them, that's 0. So r prime cross t is 0 because t is just r prime normalized. Cross product of parallel vectors is always 0. Okay, so I'm left with r prime cross r double prime is the length of r prime times r prime cross t prime. Okay, so now I'm going to take the length. Two vectors are equal. They have to have equal length, of course. So the length of r prime cross r double prime is the length of r prime times the length of r prime times the length of t prime times sine theta. So right here I'm using the fact that we learned about last week, that the length of the cross product is the product of the lengths times sine theta. Okay. Now, what else do we have? So yesterday, we talked about when you have a vector function whose length is constant, that implies it and its derivative are perpendicular. So we had that picture of a curve trapped on a sphere. So if you're, or whatever, we could just think a circle. If your curve is trapped on a circle, then your position vector looks like that, and your tangent vector looks like that, and they make a right angle. So constant length vector functions are perpendicular to their derivative. And so the whole point of this t, this capital T, is the unit tangent vector. It always has length 1. So therefore t prime and t are perpendicular. And combine that with the fact that we already said before that t and r prime are parallel. Those two together tell us that, well, r prime and t prime are perpendicular, so theta is pi over 2, and so this is 1. So it turns out that the length of r prime cross r double prime is the length of t prime times the length of r prime squared. Just using the fact that sine theta is 1, and then therefore we're done. The curvature, remember, is the length of t prime over the length of r prime. So we saw that the length of t prime is length of r prime cross r double prime over length r prime squared, but then there's an additional length r prime in the denominator, and there we go. So again, you're not going to need to know how to do this, but it ties together cross product properties, two different kinds of product rules. So it really ties together a lot of what we've talked about over the past few lectures. So it's definitely understandable from the topics in this course. But like I've said before, main thing I want to focus on is being able to use it. So as far as curvature goes, know both of these formulas, or like I said, you could just do the cross product one if you really want, and then be able to use them. All right, so I guess today's going to be a little bit of a long lecture, but let's keep going. Then you'll be all ready for the material for the exam, so you have plenty of time to study. So the next thing we want to talk about is something called the TNB frame. And so the TNB frame is relevant when you have something like a satellite that's making observations. And you have to rectify the observations that the satellite is making with, let's call it the laboratory frame, is a term that's used in physics and engineering a lot. So essentially this TNB frame you want to think of as a moving coordinate system. So let's say you have a satellite and the direction that it's going, let's say that's one of the axes. So I'm a satellite, I'm going around whichever direction I'm going, the direction right in front of me, I'm going to call the t-axis, or that's like the t direction. And I don't just have the t, I have two other vectors, we'll call them n and b, we'll name those in a second. And essentially we want these to be analogous to our standard basis vectors I, j, and k, but that they just move along this given curve. So at each point on the curve you have t, you have n, you have b. And so we want them to satisfy similar properties to I, j, and k. So for example, we want them to always be length 1 vectors, and we also want them to be perpendicular to each other, right? Because I and j are perpendicular, I and k are perpendicular, j and k are perpendicular. All right. And so it's not a coincidence that we're using capital T again. Basically, this T is going to be the same T as before. And so we've talked about how T is just the tangent vector normalized, so it's going to point in the direction that your satellite is moving. And then essentially we're going to define N to be the vector T prime normalized. And so it's going to end up pointing in the direction that the curve is turning. So if your particle is going this direction, in that way along that blue curve, the N is pointing perpendicular to T, but in the direction that your satellite is turning. And then finally, B is going to be the cross product of T and N. So these are the three formulas that you're going to need to know. And yeah, so T is just R prime normalized, N is T prime normalized, and B is T cross N. And they give you a moving coordinate frame along your curve. So let's make sure that these do everything that we say they do. So there's three of these that are immediately obvious. So T having length 1 and N having length 1 is clear. And I guess also that T perpendicular to B, N perpendicular to B are all obvious from the definition. So why is that? I'll just look at it. The length of T is the length of R prime over the length of R prime, which, yeah, that's 1. We've defined T to be a normalized vector, so it has length 1. Similarly, N is T prime over length T prime, so when I take the length, I still get 1. And then remember, the whole point of the cross product is it gives you something that's perpendicular to the two things you crossed. So since B is T cross N, T and B are perpendicular, N and B are perpendicular. So anyway, the only things that are going to take a moment to figure out are the fact that B is length 1 and T is perpendicular to N. So these are a little bit trickier. to verify. But how does that work? So it's similar arguments to we had in the previous derivation, that because t is length 1, the derivative of a constant length vector function is perpendicular to itself. So t is perpendicular to t prime because the length of t is always 1. But if you look, n is simply t prime normalized. So n and t prime are parallel vectors, which means that t is perpendicular to n. And then finally, by definition, the length of b is the length of t times the length of n times sine theta. Length of cross product is product of the lengths. Sine theta, well, t and n are both unit vectors. T and n are perpendicular to each other. So sine of pi over 2 is 1. So 1 times 1 times 1, most days of the week is equal to 1. And there we go. So as far as using Tn and B, I don't think I'm going to do it. Okay, I'll go a little bit quickly. You guys could slow it down upon rewatch. But let's just find Tn and B for the same helix that we've been dealing with. So r prime is minus sine 1 cosine. Length of r prime, we've seen a couple times so far, is the square root of 2 after you hit it with the Pythagorean theorem. And so t, which is r prime normalized, is minus sine t 1 cosine t over square root of 2. So that's t of t. T prime is minus cosine 0 minus sine over root 2. Length of t prime, hit it with Pythagorean theorem, you get 1 over root 2. So n is t prime normalized. So yeah, minus cosine t 0 minus sine t. And then b of t is t of t cross n of t. So I like to remember this Big Ten network, what channel the football games are on. So b equals t cross n. And so this 1 over root 2 that shows up in the formula for t, you could put out front. So remember, one of those properties of cross product is that like CA cross B is C times A cross B. So you might not have thought much of that when we talked about that, but effectively what that allows me to do is write that 1 over root 2 out front, as opposed to having to put it in the denominator of all 3 of those components. I'm lazy, that's annoying. This is a cleaner way of writing it. And so you end up getting 1 over root 2 times, what is this going to be? Minus sine t, minus cosine squared t, minus sine squared t is minus 1. And then 0 minus negative cosine t is that. And there we go. That is T, N, and B for our helix. Okay. Question is, should n have a root 2? No. So it went away. Sorry I didn't show that, but when I do t prime over the length of t prime, they cancel. But the reason I'm also very confident of it is that if I do the length of n, I get square root of cosine squared t plus sine squared t, which is 1. Which, remember, these are all supposed to be unit vectors. So yeah, like you said, so yeah, the question is, did I forget a root 2 in n? And the answer is no. So it cancels when you do that division, but then also it wouldn't be a unit vector if it was there. So again, remember, we want all of these vectors to always be length 1. All right. And then the very last little thing about 13.3 is the normal and osculating planes. So at each point on the curve, we could define 2 planes. And so intuitively, the normal plane does the worst job of containing other nearby points on the curve, and the osculating plane does the best job. So what on earth do I mean by this? So let's say I have this curve, and I want the normal plane at that point. So essentially normal, as you've hopefully started to pick up on, one meaning of normal is perpendicular. So the normal plane is perpendicular to the curve at the point at which we draw it. So that's what I mean by it does the worst possible job of containing other nearby points on the curve, because the curve is sort of going directly through it. So to move away from this paper, I shouldn't go like this. I should go perpendicularly away. So the normal plane, when you think about it, should have the normal vector either r prime or t. Remember, those are parallel vectors. So tangent vector, unit tangent vector, that should be what we use for the normal plane. So the osculating plane does the best job of containing other nearby points on the curve. So if you read the book, it mentions that from the Latin, I guess osculate is Latin for kissing. So this is the plane that kisses the curve at a given point. So the best way I could think about drawing it is, so, you know, some curves live in planes. We talked about that very briefly, that, like, you know, if you have a planar curve, so some curves live in planes. So if I have a planar curve, the osculating plane is the plane containing the curve. But not all curves are planar. That most curves, if I just randomly wrote down an equation, it's probably not going to live in a plane. So the best we could do is stay close to the curve. So let's say that our curve doesn't live in the plane, but the idea is that we want to have it sneak past this osculating plane and stay very close to it. So like if, I guess our fingers are planar, right? I'd have to, well, I don't know. I guess not if you look at this slight bend here, but essentially you want to think of the osculating plane as the curve is just sort of sneaking right through it. So that's what I'm trying to draw in this picture here, that you see those dotted lines, it's coming underneath that plane and staying very close and then just kind of sneaking past. So take this picture and just sort of bend that curve so that the front half of it is sort of below that plane and then the upper half is just above. So that's the idea of the osculating plane. And so to do the best job of containing other nearby points, basically you want t and n to point along the osculating plane, which means that the cross product b, which is t cross n, should be perpendicular to your osculating plane. So t is the direction of the curve, n is the direction that the curve is turning, and remember t and n are always perpendicular. So if those point along your osculating plane, the binormal vector b points perpendicular. So I'm sure I have it written down. I now realize that maybe I never said binormal vectors. So yeah, t is unit tangent, n is unit normal, b is unit binormal. And so I think we asked a couple homework questions on that, just applying some of those things. So this is probably the longest lecture all semester. Sorry about that. I probably should have done some of 13.3 yesterday, but 13.4 won't be too long. Let's try and get through this. So 13.4 talks about some vocabulary and then something called components of acceleration and Kepler's laws. So Kepler's laws, we're not going to do it all. I'm not going to talk about it today. It's pretty neat. Essentially, you guys know enough to understand how the orbit of planets in our solar system are, how they behave. So that's pretty neat. Components of acceleration, I will discuss it, but it's not on quiz or test. It sort of ties together some of the things we've been discussing in a nice way. So I do like to discuss it. It will be on the homework, but don't worry about memorizing the formulas for the quiz or the test. So really the big thing to worry about from this section is just some vocabulary. And so we've hinted at some of this before, that r you want to think of as position of a particle, r prime, you know from physics that the derivative of position is velocity. And then the length of velocity is something called speed. So the length of r prime is the length of v. We'll call that then scalar v, right? So remember, we're careful. And we use vector notation for things that are vectors. So if you see a v that's bold or with a little vector arrow, then that's velocity. Whereas if you just see regular v, that means it's a scalar and that we're talking about speed. And then finally, acceleration is a vector, and it's the second derivative of position or the first derivative of velocity. So honestly, that's the vocabulary. This is really all you're going to need to know from 13.4 for the exam. And so just make sure you practice on the homework. You should be okay, but you'll do some problems using these words, but there aren't really any new types of calculations, so I'm not really going to go through anything like that. I just want to talk about this last topic called components of acceleration. And so the idea is that we have our acceleration a, which remember a is r double prime, and we want to express it in terms of our moving coordinate frame TNB that we talked about a few minutes ago. So the tangential component of acceleration is a sub t, the normal component is a sub n, and the binormal component is a sub b. And so it turns out we're going to be able to get equations for these three components of acceleration, and they're going to be instructive as far as what's going on. So it turns out that you never have any acceleration in the binormal direction. So the binormal component of acceleration is always 0. It turns out that the tangential component is the derivative of speed. So speed, remember, is v, the length of r prime. And so, yeah, it turns out that that's the tangential component. And then it turns out that the normal component is curvature times speed squared. So kappa v squared, using our new notation for speed, is just scalar v. And I think this is neat, so let's zoom out a little bit so you can see here. And so this really explains the forces that you feel when you're driving in your car. So, okay, you've learned in physics class that acceleration is change in velocity. So what's velocity? Velocity is a vector. What is a vector? A vector has speed and direction. So when you're driving in your car, and then I guess you also learned in physics that acceleration and force are very closely tied together, right? F equals ma. So the force that you feel is basically proportional. Well, it is proportional to your acceleration. So the acceleration that you feel when you're driving, that's the forces that you feel. And so one of the types of forces that you feel are when you change your speed. And so how do you change your speed when you're driving? Well, you slam on the gas pedal or you slam on the brake. So what happens when you slam on the gas? You feel acceleration. I can't tell where my camera's at. You slam on the gas, you feel acceleration like that. So that's in the direction that you're going, right? You slam on the gas, the equal and opposite reaction, whatever, you end up feeling like that. If you slam on the brake, you feel acceleration directly forward. So forward and backward, that's the direction that you're moving. So, and that's what's this is meaning right here, that it's in the direction that you're going. So when you're driving in your car, yeah, the unit tangent is just straight ahead. And so gas brake acceleration is that force that you feel, and it's going to be depending on how much you slam on your gas or your brake, that's how large the derivative of speed is, right? So if you are accelerating, if you're speeding up, then that's positive, which means that your acceleration is forward, whereas if you slam on the brake, your speed is decreasing, which means it's backwards. So that makes sense from what you feel in your car. And then, okay, what's the other thing that you can change about your velocity vector? Well, you can change its direction. How do you do that in a car? Well, that's your steering wheel, right? And so when you're steering, you feel left and right forces. So that's perpendicular to the direction that you're going. Like, remember, the whole idea is that when you're taking a curve, T is going to be the direction you're going, and N is the direction that you're turning. So when you're steering, you feel the left and right forces. And okay, to what extent do you feel left and right forces? Well, it turns out it's proportional to how tight of a curve you're taking. So kappa, remember, is the curvature. So the tighter curve you're taking, you feel more left and right forces, right? So if you're taking a very tight curve, you have a greater value of kappa compared to if it's a more gradual curve. So the degree that you feel left and right forces depends on how tight of a turn you're making, but then also it depends on how fast you're taking that curve. And so it turns out it's not proportional to speed, but it's actually proportional to speed squared. So that's why, I guess you talk about G-forces when you're making turns and you're on a fun roller coaster or something like that. The faster you go, it turns out that the amount of force that you feel is proportional to speed squared. And so then finally, if you're driving on flat ground, that's why you don't really feel any up or down forces, is that the binormal component is 0. So T is where you're going, N is where you're turning, and then B is that cross product, which when you're driving in your car would be up or down. Okay. And so that's neat, that formula. It sort of ties together what you feel when you're driving. And then it turns out that you could show that these formulas are equal to this. It's actually, I'll just show you. I'll show this real quick. It's a very similar formula to what we had before. So like using our new notation, velocity is speed times unit tangent vector, because remember T is r prime normalized, which is velocity divided by speed using our new notation. And so then if I take the derivative, this is the same calculation we did earlier. The derivative of velocity is acceleration. So that's derivative of speed times t plus speed times the derivative of t. And then remember, n is t prime normalized. So if I substitute in, A is v prime t plus v times length t prime times n. But then remember, kappa is length t prime over length r prime, which is length t prime over v. So length T prime is kappa times V. So that's where we got V prime T plus kappa V squared N. So that was our starting point that we had up there, that A is speed prime times tangent unit tangent plus curvature speed squared times unit normal. So that's really just the same product rule in our definitions that we've been working with. And then you use that formula for curvature. Remember, curvature is going to be R prime cross R double prime over length R prime cubed. But then, yeah, just remember that length R prime using this new notation is speed, so that explains that. And then, it's really just the chain rule that the last thing we have to do is confirm that the derivative of speed is the dot product of R prime and R double prime over the length of R prime. And so, why is that? Well, speed is the length of velocity, which is the square root of V dotted with V. And that means that the derivative of this is 1 over 2 times the square root of V dotted with V times the derivative of the inside, which is V prime dot V plus V dot V prime, which then if you substitute everything in, this is 2 R prime dot R double prime. This here, that's a V itself, so length of R prime, and the 2's cancel, and so you get, yeah, R prime dot R double prime over length R prime. So essentially it's, yeah, just some chain rules. But again, that stuff, feel free to ask in recitation about that if you want to see that a little bit slower. The book goes through it as well. Those formulas are on the homework, but don't worry too much about where they came from. But I do have a question. So T and B is X, Y, and Z. Yeah, kind of like that. I mean, so X, Y, and Z, you want to think of as just being fixed, that the origin is always located at the origin. But then the whole idea is that now let's instead say we're launching a satellite and it has its own coordinate system, and we want one of the coordinates to basically be the direction that it's going, right? So if your thruster is on the back, then that's going to be how it works out. And so it's important for satellite motion and things like that. And the gas in the brake, depending on which direction you're going, your gas doesn't always make you go north, right? You hit the gas pedal, the direction is whatever direction you're going. And so essentially that's the advantage of all this, of keeping track how acceleration behaves along these moving vectors. So anyway, it's just a neat thing to think about, that because when you're in your car, the car itself is moving, but like your perspective in the car is fixed. That as far as you're concerned in the car, there's this notion of front, back, left, right. Well, front, back is basically your tangent direction. Left, right is your normal direction. And then up, down is your binormal direction. And so, yeah, just think about the perspective you have in your car as being a moving coordinate system. Front, back, left, right, up, down. So anyway, that is that. I think you talk about some of this stuff in Physics 211, those of you who have done that. Normal force and things like that. But anyway, that's chapter 13. Sorry about the length of that, but wanted to get it in on Tuesday, so you have plenty of time for the exam. But any other questions before we wrap it up? Yeah, it would stay the same. That I mean, I guess it even stays the same in your car, right? That like if you're driving up a hill, uh, you know, your turning is sort of at this angle, and then your front and back is at that angle, but then you wouldn't feel any force like that. So I guess if you define up and down to be vertically from the, perpendicular to your car chassis, you'll never feel force like that. So yeah. Alrighty, I guess I will stop this recording then. But hang out if you guys have any other questions. But I will, I guess, see you next week. You won't see me before the exam, so good luck on that. And have a good week.